So for this question, just to be clear, they're actually done us a big favor here. They've told us here that the test statistic of z is 1.75, and we have some claim that the proportion is greater than 6%, or sorry, 60% or 0.6. So there's a formula, right, for the to find the test statistic, which is something like this. Right, so for this problem, they've done us a big gift, and they've just told us don't worry about calculating this. It's just 1.75. So we've done that calculation for all that, and we got 1.75. So this is a good question because it saves you a little bit of time and makes sure you just get to the point of understanding rather than calculating. So what you do here is we know that we're looking at a normal distribution here, and we know that our z is over here. It's 1.75. Alright, so we're testing the claim that some proportion is greater than 0.6. So this could be that a proportion like this might be something like a proportion of voters in Wyoming that voted for Republican for president would be greater than 60%. We want to prove that it's greater than 60%, and we went out and we asked a lot of people who they were going to vote for, and we calculated z and got 1.75. Alright, so when you're trying to prove that it's greater than that, then you're having to look at what's the chance that I got, right here, 0, if it was exactly 0.6, and you went out and you interviewed people in the state of Wyoming and asked who they voted for president, if it was exactly 0.6, then your z-score would be 0, which says that, yep, it's exactly what I told you it was going to be. It was 0.6, and so therefore your z-score is 0. We're trying to prove that it's greater than 0.6, and we got z is 1.75. So what we're trying to prove here is that this area right here is only, this basically in one sense represents a percent chance of getting a result like this. In other words, if this thing was all true chance, the chance of getting something greater than 0 we know would be 50%. That's half the curve. Right, so you got a 50% chance that the true proportion of voters would be greater than 0.6, and there's a 50% chance that the proportion of voters would be less than 0.6. It just breaks it down evenly. So basically, and that's one thing I don't like about this problem, we've basically proven that there's way more than 60% of people voting. If this number, this calculation here, if it works out to be 1.75, that means there was way more than 0.6. All right, and that's what we're trying to prove, is that p is greater than 0.6. But we have to prove it. We have to quantify what is way more. Way more is basically we want to have an area to the right of 0.5 or less. All right. So the further this number goes over 1.75, if it went on over to 2 and 3 and 4, this area would get smaller and smaller and smaller, which means that we're way more than 0.6. Alright, so that's what we're getting at here. So we're basically seeing how far can I push this line over until I get this area. This area needs to be less than or equal to 0.05 for me to be able to say that it is, we'll just keep using my words there, way more than 0.6, or what we would say is statistically significant. Alright, and I misspelled statistically there. So that's what we have to do. Now back to the original question, what is the p-value? You can do this with a calculator. Now keep in mind the calculator normally computes area to the left. We want to do area to the right, so that means we have to do 1 minus, and we're going to do second bars and get distribution, and we're going to do normal CDF 1.75. Sorry, I got that wrong. It's 1 minus, I forgot, I have to put my lower limit. So it is normal CDF, but remember you have to put your lower limit. We put some really small number like -9,999 to 175. And we find that the area represented by that little piece is 0.04. And then part B is asking, what is the critical value of z? In other words, what is this z value when the area is 0.05? So using inverse norm 0.95, we find that it's 1.645.